Today we will start with halogenation of enolizable aldehydes and ketones. Aldehydes and ketones which have alpha hydrogen atom can only aldehyde and ketones which contain alpha hydrogen are only can enolize, that is, the aldehyde and ketones with alpha hydrogen atom are able to get enolizable, that is, they can form enols. So these compounds with halogen in the presence of acid or base gives alpha halogenated products, that is, the alpha carbon gets alpha hydrogen is replaced with hydrogen atom, so we get halogenated product. So in this, aldehyde or ketone with halogen in the presence of acid or base gives alpha halo aldehyde or alpha ketones. This mechanism can take place in the acid or in the presence of base. So these are the acid catalyzed or base catalyzed. So first we start with base catalyzed, or say base promoted halogenation. It is base promoted halogenation, and in the case of acid is acid catalyzed halogenation. So what is the difference between base promoted or acid catalyzed? We will be concluding in the end. So in base promoted halogenation, all the alpha hydrogens are replaced with halogens. That is, if we take up acetone with bromine in the presence of base, we get this one hydrogen is replaced with bromine. If we continue this, then second hydrogen is also replaced with hydrogen, and if we further continue, then all the hydrogens are replaced with halogen. So we get alpha tribromoacetone, that is, all the alpha hydrogens are replaced. So mechanism for this is in the presence of base, that is, base abstracts this alpha hydrogen and we get this carbanion. This carbanion is resonance stabilized, it can be changed into enolate ion, and then this attacks the bromine, and when attacks with bromine gets attached with the carbon carrying the negative charge, that is, and Br is attached to this carbon with negative charge, that is, we get alpha bromoacetone. And then if this step is repeated, then second hydrogen will be replaced, then third hydrogen will be replaced, and so in if the reaction is done with acid, then we say it acid catalyzed, not acid promoted. So in this, the reaction with in the presence of H positive, this alpha hydrogen is again replaced with halogen. So mechanism is, as we know, in the presence of acids, first the protonated ketone is formed, and then this ketone releases hydrogen, that is hydrogen, and then the enol is formed, and this enol, that is, this carbanion, is resonance stabilized or it is dynamic equilibrium with enol. Now this enol combines with halogen to give this product in which through these electrons Br positive is attached, and these electrons move to this to uh, complete the valency of carbon, and gives further this further gives this as a final product in which this hydrogen is removed as H positive. So in this, the H which is present in the starting is released in the end. The hydrogen which is used in the starting, that is this, is released in the end. So it is a base catalyzed halogenation. But in the base, in the presence of base, when we treat it with base, then we get in the end we do not get OH negative. So OH negative is not released in the so this OH negative started the reaction and then it is not involved in the reaction. So it is a base promoted mechanism, but in that acid is first utilized and then in the end it is released. So it is acid catalyzed, but first mechanism is base promoted, because base only abstracts hydrogen and then that is not involved in the reaction. So this is the halogenation of aldehydes or ketones with alpha hydrogens, in which all the alpha hydrogens are replaced with halogens. So next we take up bimolecular reduction. Bimolecular reduction means two molecules are reduced in the presence of some active metals like magnesium, and this reaction is to give pinacoles. So in this we take up this acetone with magnesium amalgam and benzene. It gives this magnesium salt of pinacol, in which two molecules of acetone are condensed in the presence of magnesium active metal and forms this cyclic intermediate, which upon hydrolysis gives this pinacol, that is diol, and this reaction is called pinacol reduction. So mechanism is, first, this magnesium, that is Mg2 positive, Mg has active metal, Mg has two lone pairs. Otherwise in the reactions we generally use Mg2 positive, but it is here magnesium metal itself is used, that is it has two valence electrons, and through these single electrons it forms bond with this oxygen and with other oxygen. And here these pi electrons, that is pi electrons of double bond, can be shown as two electrons, which if one move to this, one move to this, and this electron and this one electron forms bond, that is this. Similarly on the other side this is formed, and then this is, these single electrons further form bond, and then this cyclic intermediate is formed, which upon hydrolysis gives this diol. So this is the bimolecular reduction in the presence of magnesium amalgam to give the pinacols. So next topic is alpha beta unsaturated aldehydes and ketones. So till now we have done all about aldehydes and ketones only. Now the next is alpha beta unsaturated aldehydes or ketones, that is these are the aldehydes and ketones, but in which double bond is present at the alpha beta position, that is this is alpha and this is beta. This is alpha carbon, this is beta, that is between alpha carbon and beta carbon double bond is present. So these are alpha beta unsaturated aldehydes and ketones, that is double bond between alpha and beta carbons. So this IUPAC name can be written as prop 2 in 1Al for this but 2 in 1Al. This we have already done the IUPAC naming. So next is structure. So structure is the carbon carrying C double bond O group, this group. Then to the next carbon, alpha and beta carbon, there is a double bond. This is most stable structure. So the resonating various resonating structures are, if the electrons move to oxygen and then these electrons move to this, so this structure is formed. This structure in which this carbon has positive charge and oxygen has negative charge. In this positive and negative charge are very close to each other, so this structure is least stable. And then the other resonance structure is if these electrons move to this, so we get this, and in this the positive charge and negative charge are far away, so it is less stable because this structure has charges, so it is less stable, that is it is more stable than this structure in which these are very close to each other. Positive and negative charge are very close to each other, in this they are somewhat far away, so this structure is less stable. So next is, we can write the resonance hybrid structure as this. So in this, the stability of various structures, that is these structures is, first structure is more stable because it has no charge separation. In second structure, positive and negative charge are closer to each other, so it is least stable, and the last structure is less stable because in this the positive and negative charges are somewhat far away. So out of these structures, first is more stable, then last structure, then comes the central structure, that is it is least stable. So next comes the preparation. These can be prepared by aldol condensation or by Claisen condensation. These reactions we have already done in aldehydes and ketones, so we will not repeat these reactions. So next is the properties. In these properties, in the alpha beta unsaturated aldehyde and ketones, the main reactions are electrophilic addition reactions and then the nucleophilic addition reactions. In electrophilic addition reactions, the electrophile attacks. So the electrophile when attacks, it depends upon the reactivity of aldehydes and ketones. So alpha beta unsaturated aldehydes and ketones, these are less reactive. These are less reactive than simple alkenes, as we have already done also, that is in aldehyde and ketones we have mainly done nucleophilic addition reactions. We have not electrophilic addition reactions because aldehyde ketones are less reactive towards the electrophilic addition reactions. They generally undergo nucleophilic addition reactions. So in electrophilic reactions, that is addition of bromine, addition of HX or per acids, they react very slowly. And second comes the, mainly we will be dealing with nucleophilic addition reactions to alpha beta unsaturated aldehydes and ketones, and they can take place in two ways because they have two positions to join to add the attacking reagent. The addition can be 1,2 addition or can be 1,4 addition. 1,2 addition means the attacking reagent gets added across the double bond, and in 1,4 addition, first is one atom is attached to one side and the second part of attacking reagent gets attached to the fourth carbon or fourth atom. So 1, 2 and 1,4 addition takes place in alpha beta unsaturated aldehydes and ketones. So that is why we say that two ways can addition take place. First is direct addition. If direct addition means instant addition, when instant addition takes place, it is generally 1,2 addition. In 1,2 addition, we can show nucleophile when attacks, then it attacks the carbonyl carbon, electron moves to this, so oxygen carries the negative charge and nucleophile attaches to the carbon. So it is, suppose it is first carbon. Now the second part, that is suppose H positive attacks the O group, so 1,2 addition takes place. The attacking the group attached to adjacent positions, one attached to carbon, other attached to O, so 1,2 positions, so it is 1,2 addition. Is simple or direct addition, or it is 1,2 addition. Second is conjugate addition, or it is 1,4 addition. 1,4 addition, that is we can show this nucleophile now attaches the fourth atom, 1, 2, 3, then 4th. The nucleophile is attached to 4th atom, and then these pi electron moves to this carbon and then to oxygen. So the oxygen now carries the negative charge after the addition of nucleophile. So it is first 2, 3, 4. First carbon and then the 4th atom has negative charge. So other part, that is H positive, will now get attached to this oxygen carrying negative charge. So it is this. So in this addition has taken 1 4 addition. One is attached to first carbon, so say, and the other to fourth atom. So in this way, it is OH. So in this way we can easily write, and it is enol in which the carbon carrying double bond group has OH group also. So it is enol, and it is in dynamic equilibrium with this keto form in which hydrogen shifts takes place. So this is the 1,4 addition. It is also called conjugate addition, like conjugation, conjugating bonds. Now the factors which will govern 1,2 versus 1,4 additions, that is, in a particular reaction the 1,2 addition will take place or 1,4 addition will take place. This depends upon the various factors. Like first is reactivity of carbonyl carbon. Reactivity of carbonyl carbon means the carbonyl group is of aldehyde or it is of ketone. We have already done that aldehydes are more reactive. Therefore in this 1,2 addition takes place. The instant addition will take place, and in instant addition 1,2 is only possible. Whereas if we take up addition of HCN to this alpha beta unsaturated aldehyde, that is acrolein, then the CN group is attached to carbon, and H is attached to oxygen, that is OH is formed. So if we take up another example, that is the addition of Grignard reagent, and then further upon hydrolysis, then we get this CH3 group is attached to carbon, and this OH is attached to this next carbon, and we get a 1,2 addition product. Similarly, ketones being less reactive, they have 1,4 additions. That is, if the addition of this takes place to a ketone, that is ketone C double bond O, and it is alpha carbon, it is alpha beta unsaturated ketone. In this, if addition of HCN takes place, then CN group adds to this carbon, and then OH is attached to this carbon, and further upon changing into equilibrium, it gives the keto again. So this is the 1,4 addition. So next is similarly addition of secondary amine to this. In this again, this group gets attached to this carbon, and H is attached to this oxygen, and then further upon hydrolysis this group is changed into keto form. So next is second factor which governs the 1,2 or 1,4 addition is reactivity of reagent. In this reactivity of reagent, that is what type of reagent is. If the reagent is strong, that is if it is organolithium is strong nucleophile, so in this 1,2 addition will take place. Like Grignard reagent, Grignard is less reactive, then it will give 1,4 additions. As now we will explain it with example. That is in this first example, that is it is a CH3Li, that is it is a strong reagent, strong nucleophile, and this the alkyl group is attached to this carbon, and then H2O group. So 1,2 addition has taken place, and then this in second Grignard reagent is there. So in this alkyl group is attached to the this carbon, that is fourth carbon, and H to this, and then further to change to keto form. So next factor is steric hindrance. In steric hindrance, again, if the carbonyl carbon is sterically hindered, it has bulky groups around it, then the addition will be 1,4. If at third position group is present, then it will have 1,2 additions. So taking up example, in this example we have taken this. This is first carbon, carbonyl carbon, then second carbon, then third carbon. In this, the second carbon has bulky group, phenyl group. So in this, the addition will take place at this carbon, and that is it is third carbon, but it is fourth position. That is according to first, 2, 3, and it is 4. So at the fourth position, the phenyl group is attached, and it is 1,4 addition. But if the bulky group is present at the fourth position, or say third carbon, then the phenyl group is attached to this carbon, carbonyl carbon, that is 1,2 addition has taken place. So it depends upon the steric hindrance around the carbonyl carbon. And so next is catalysis by cuprous salts. If 1,4 addition of Grignard reagent can be made to predominate if the reaction is carried out in the presence of Cu positive ions. That is, in this example, we have taken addition of Grignard reagent in the presence of CuCl and ether, that is Cu positive ions, and then the addition will take place. 1,4 addition has taken place. 1,4 addition has taken place. So in this way, the various factors can decide which type of addition will take place. 1,2 addition, that is direct addition, or 1,4 addition or conjugate addition will take place in alpha beta unsaturated aldehydes and ketones. So now the last reaction in this chapter is Michael addition reaction. This can be asked in naming reactions also, and this is important with mechanism. In this, conjugate addition or 1,4 addition, conjugate is also called 1,4 addition, of carbanion to double bond of alpha beta unsaturated aldehydes or ketones or esters or amides or nitroethylene can take place is called Michael addition. And so let's take up an example. First is addition of malonic ester carboanion to methyl vinyl ketone. It is methyl vinyl ketone. In this, the addition of malonic ester carbanion, that is, first carbanion will be formed. This is the malonic ester carbanion is formed, and this is formed from this malonic ester. This is malonic ester with sodium ethoxide. In the presence of sodium ethoxide gives this carbanion, and then this carbanion attacks the methyl vinyl ketone as shown here. This is methyl vinyl ketone, and in this the addition takes place is 1,4 addition. That is, first this carbanion negative charge can come attaches to this carbon, and these electrons move to this, that is CH2, and this whole group is attached. And then in the presence of alcohol, it abstracts hydrogen. This oxygen carrying negative charge will abstract, that is this electron move to this, and this oxygen now with negative charge abstracts a proton from the alcohol, and we get this product, and in which is in tautomerizes to this, that is enol and keto forms are interconvertible and they tautomerizes to be converted into each other, they are in dynamic equilibrium. So this is the example in which the malonic ester carbanion, which is formed from malonic ester in with sodium ethoxide, and this carbanion attaches with this methyl vinyl ketone, and then the addition is 1,4 addition, that is this whole group is attached to the this fourth atom, this is attached to this fourth atom, and this is first atom, and this is fourth atom. So this whole group gets attached to the fourth, and to the oxygen hydrogen is attached in this way, and then it tautomerizes to the keto form. So in this 1,4 addition takes place. We can also show this with other similar reactions, that is addition of ethyl cyanoacetate to ethyl acrylate in the presence of sodium ethoxide. Sodium ethoxide basically abstracts the hydrogens. That is, now this is the ethyl acrylate. When it combines with this ethyl cyanoacetate, in the presence of this abstracts the proton from this, and then carbanion is formed, and that carbanion gets attached to the this carbon, that is this is attached, and the H is attached to this carbon, and then further into keto form is changed, so we get this as a final product. So similarly, if addition of nitromethane to acrylonitrile in the presence of sodium ethoxide, so first sodium ethoxide abstracts proton from this, and then this group gets attached to this carbon, that is fourth position, that is this group is attached, and we get this 1,4 addition product. So this is all about the Michael addition reaction. Michael addition reaction is important, it can be asked with example, so you must know at least 2 examples in which Michael addition takes place, that is addition with 1,4 addition or conjugate addition takes place. So it's all about aldehydes and ketones, and with this unit is complete. Next we will start with next units. So thank you.